These are examples for section 9.1, Similarity. Example 1. In the triangles at the right, triangle RST is similar to triangle NMP. Recall that for two triangles or polygons to be similar, the corresponding angles must be congruent, just like they are with congruent triangles. But the sides, the corresponding sides, instead of them being congruent, corresponding sides in similar figures are proportional. Proportional, again, means that they create, each corresponding pair of sides create ratios that are all equivalent to one another. So back to the problem, triangle RST similar to triangle NMP, you can either keep track of the corresponding parts by the statement, the similarity statement, or you can keep track of it by the diagram. Starting with part A, what are the pairs of congruent angles? Just like with congruent triangles, we find corresponding angles congruent. So starting with angle S is congruent to angle M. Notice S is in the middle position, so is M. Another angle, angle R, is congruent to angle N. Again, R is in the first position here, corresponds to the first position there. And finally, angle T is congruent to angle P. T and P. Again, when it comes to side lengths, corresponding sides are proportional. So, B, what is the extended proportion for the ratios of corresponding sides? Remember, an extended portion is simply a proportion that has more than two ratios. It can have 3, 4, 5, or more. So, as we go through the corresponding sides, let's start with ST. The length of ST must correspond with the length of, either use the diagram or come up here. ST are the last two. So MP is what they correspond with. So ST is to MP as, another side, SR, the length of SR is to side MN, the length of MN. As, the last side, RT, right here, first and last, is to, first and last here, NP. NP. And so here are all the corresponding pairs of congruent angles, and here are the corresponding side pairs in an extended ratio. Example 2. Are the polygons similar? If they are, write a similarity statement and give the scale factor. Part A, JKLM and TUVW. We're going to check to see if these two polygons are indeed similar to each other. Again, they have to have all corresponding pairs of angles congruent, and they've all got to have corresponding side lengths proportional. So starting with identifying pairs of angles, step 1, we start with angle J is congruent to, coming over here to T. Since T has the same number of arcs on it, they are congruent. Another pair of angles, K, angle K. The right angle is congruent to its corresponding part, angle U. Going on to angle L in the first figure corresponds to angle V in the other one. So L has 3 arcs, V has 3 arcs, so they are congruent. And finally, the last pair of angles, angle M. Looking over here, it has 1 arc. It's supposed to be congruent to angle W because they're in the same positions, and it is. So those are congruent. So far all the angle pairs are corresponding and congruent. Now we go on to the ratios of corresponding sides to see if they're proportional. I'm going to start with JK is to TU as KL is to UV as LM is to VW as the last pair, JM, first and last, is to first and last here, TW. Now we're going to see if these really are equal by coming over here and using the actual links, the numerical links. So JK is 12, is to TU, which is 6, as KL is 24, is to UV, which is 16, as LM, right here, is 24, is to VW, 14, as JM, which is 6, is to TW, 6. At this point, to see if these are equivalent, we simply reduce them. 12, 6 reduces by 6. 6 goes into 6 once, 6 goes into 12 twice. This is 2 to 1. 24 sixteenths reduces by 8. 8 goes into 16 twice. 8 goes into 24 3 times. And already we can see that 2 to 1 is not equal to 3 to 2. Continuing on just to see what happens, 24 fourteenths, it reduces by 2. 2 goes into 14 7 times. 2 goes into 24 12 times. Definitely not similar because these are not going to be equivalent. 12 to 7, 3 to 2, 2 to 1. Finally, 6 to 6 reduces by 6, and we get 1 to 1. So all of these ratios are different, but even if just one of them was different and all the other three were the same, it destroys this comparison, and you would not have similar figures. So we conclude by saying that quadrilateral JKLM is not similar to quadrilateral TUVW. And we can't write a scale factor because there is no common scale factor because these aren't similar. Going on to part B, we want to look at triangle ABC and triangle DEF. We want to see if these are similar, and if so, write a scale factor. Identifying the congruent angles, we start with angle C is congruent to angle F. Is that true? C and F? Yes. One arc. Angle B, see if it's congruent to the one in the middle position here, angle E. B and E both have 3 arcs, so yes, angle E and B are congruent. And finally, angle C, and the last one, angle F. Angle C has 1 arc, angle F has 1, oh, not C, A and D. Angle A, which has 2 arcs, and angle D, which has 2 arcs, they do correspond and they're congruent. So far we have 2 pairs. So far we've got all the corresponding pairs of angles congruent. Let's see if the sides are proportional. Starting again with AB, side AB should be to DE as, back over here, BC is to EF, as AC is to DF. Let's check and see if these are actual proportional, an extended proportion. AB is 12, is to DE, which is 15, as BC, which is 16, is to EF, which is 20, as AC, which is 8, is to DF, which is 10. Now let's check and see if all of these simplify or reduce down to the same thing. Okay, so with 12/15, we can reduce that by 5. 5 goes into 15 3 times. 5 goes into 12 excuse me, 3. 3 goes into 15 5 times, 3 goes into 12 4 times, 4 to 5. In 16/20ths, 4 will go into both of them. 4 goes into 25 times, 4 goes into 16 4 times. So again, we have 4 to 5. So far, we're on our way to showing similar figures here. And finally, 8/10 reduces by 2. 2 goes into 10 5 times, 2 goes into 8 4 times. Since all 3 of these are 4 to 5, then 4 to 5 is our scale factor, K, or we can write it 4 to 5. Finally, we say that triangle ABC is indeed similar to triangle DEF. So there's our similarity statement, and there's our scale factor. Example 3. In the diagram at the right, ABCD is similar to EFGD. ABCD is similar to EFGD. Now, in this problem, unlike the first two, they're telling us that these two are similar. So we're not testing to see if they're similar. We already know they're similar. They're asking, what is the value of X? It's right here. When this happens, use the fact that similar figures have corresponding proportional sides. And all we really need are 2 sides in this particular problem. And one of them has got to include what we're looking for. One of the ratios has to have both parts of the ratio have to be numbers. So let's go ahead and start with FG, since that's what we need. The length of FG is to its corresponding part. FG corresponds to BC. So FG is to BC as, now when we do this other part, we need to make sure that we have both corresponding sides, numbers for both corresponding sides in both figures. If we try to use AB and EF, obviously we can't because we don't know what Y is. So that's out. We can't use DC and DG, even though they correspond, because there's nothing for those two. The only one we can use are these two. For ABCD, we can use AD is to ED. Let's see, it would be the other way around. ED is to AD. Now you'll notice I switched those around because I started with the smaller figure up here to the larger one. Smaller to the larger. And then we substitute in those values. So FG was X. BC was 7.5 or 7 5/10 equals ED, which is 6 right here. And it corresponded with AD, which is 9. Then we cross multiply or use cross products. Now remember, you can only use cross products when you have a ratio or fraction that equals another ratio or fraction. This is the only time we can cross multiply or use cross products. So we have x times 9, or 9x, equals 7.5 times 6. Then by solving for x, we have 9x equal 7.5 times 6 is 45.0 or 45. Then divide both sides by 9, and x is 5. So the value of x in this problem is 5. Example 4. In example 4, on your notes, there's a drawing of the bridge, a diagram of the bridge. This one that I have right here is a lot larger for this particular video. I needed to make it larger. So when you do your own on your paper, you're going to measure your own, which is going to be a different length than this. It's going to be a lot longer. So I'm going to use the length that you have for your notes. Example 4. The diagram below shows a scale drawing of the Golden Gate Bridge. The distance between two towers is the main span. It's called the main span. So the distance between this tower and this tower is called the main span. What is the actual length of the main span of the bridge? The actual length. When dealing with scales, from blueprints to maps, anything like that, the scale is always measured as the model measure to the actual measure. The model to the actual. So, based on similarity, we can set up a proportion. So we can start off with, notice we have a scale. Any kind of blueprint or map is going to have some sort of scale. This scale is 1 centimeter for every 200 meters. So 1 centimeter represents the model, and 200 meters represents the actual length or distance. So we set up our first proportion using the scale. So this would be the scale ratio, which is 1 centimeter to 200 meters. We set up a proportion with another ratio. This time, we're looking for the actual length of the bridge. Well, the actual is in the denominator here of the ratio, or the second term. So I'll use D for distance in meters. Now, the model, the scale model of this bridge has to be found by measuring. So take your ruler, and since this is in centimeters, we use the centimeter side of your ruler. And so I'm using the centimeter side of my ruler, and you measure from span, from main span, the main span from post to post, or from tower to tower. And of course, yours on your copy, if you measure it, you're going to get 7.9 centimeters. 7.9 centimeters. Almost 8, but not quite. Drop the centimeters in meters. We have 1 is to 200, as 7.9 is to D. Then we cross multiply or use cross products. We get 1D, or D, equals, multiplying 7.9 times 200, we get 1,580 meters. So the actual distance of the main span of the Golden Gate Bridge is 1,580 meters. It's interesting to note that if you'd used 8 here instead of 7.9, it does make quite a difference. If you were to cross multiply this way, 1 times D is D, and 200 times 8 is 1,600. Well, that's quite a few more meters. I mean, it's a good 20 more meters than what the actual measurement that we took at 7.9 was. So it's very important that you're precise and accurate with measurements when you're dealing with scales. Example 5. In example 5, we start using the similarity postulate and theorems that you were introduced to in the lesson. The angle-angle similarity postulate, or AA postulate, the side-angle-side similarity postulate, SAS similarity, and the side-side-side, or SSS similarity theorem. And so those are the only things required to show that two figures are similar. In example 5, part A, are the triangles similar? If so, write a similarity statement for the triangles. So let's take a look at what we have here. We've got all 3 pairs of sides with numerical lengths on them. We don't have any indication that the angles are congruent in any way. Even though this looks like a right angle and this looks like a right angle, remember, we can't assume that. So there are no angles given to us. However, we have all 3 pairs of sides. So the only way we could show that this is similar is if we tried to use the side-side-side similarity theorem. So if we can show that they are all three pairs of sides, corresponding sides, are proportional, then we use SSS to show that these two triangles indeed are similar, and we can write a similarity statement. So I'm going to start with the shortest sides. I'm going to start with ST is to the shortest side over here would be, out of 15, 12, and 9, would be the VX, or I'll do XV. And so ST was 6, and VX is 9. Simplifying that by 3, we get 2 to 3 for our scale, hopefully our scale factor. Let's try the longest side. Now go through the longest side in this original triangle, since we started with the small one, is this SU, is to the longest side in this one, which would be 15, so that's WX. SU again was 10 to WX was 15. Simplifying that, reducing by 5, we get 2 to 3. And then our remaining side would be the one in the middle valued one. That's that UT is to the one over here. The middle one would be VW. UT is 8, is to VW is 12. Now if we simplify this and get 2 to 3, then we've got enough to use SSS. If we don't, then these are not similar. 8 to 12 reduces, and it reduces by 4. 4 goes into 8 2 times. 4 goes into 12 3 times. So since we've got 2 to 3 all 3 times, and by the way, that's your scale factor, 2 to 3, we can now say that triangle, and we have to do it in corresponding order here. I'm going to start with S, T, U is similar to triangle. Make sure they correspond. Since I started with S, I start with X, X, and then I move over to V and then W, by the SSS similarity theorem. Part B. Are the triangles similar? If so, write a similarity statement for the triangles. This time we have two triangles overlapping each other. We have triangle MKN and triangle LKP. And so we try to use one of the theorems or postulate that we discussed. We're trying to check to see if we can't use SSS because we don't have any indication for MN or LP. We would have to have those third sides. So SSS is out. Angle, we've got one angle here in the smaller triangle which overlaps with this same angle in the bigger one. So there's one angle. But we don't seem to have any other angles. These two angles would have to be congruent, or these two would have to be congruent. It's really easy to think that these are parallel, but there's no parallel indication on these line segments or sides, so we can't use corresponding angles here and here or here and here. So AA is out. The only one left is the SAS similarity postulate or theorem. And so let's see if we can do that. If that's true, then angle K in the smaller triangle should be congruent to angle K in the larger triangle. And so we can write something like this. Angle MKN is congruent to angle LKP. Since they're the same angle, this was by the reflexive property. So we've established one angle in both triangles, corresponding angles. Then for the other two sides on either side of it, this being the included angle, we're going to have to look at this ratio for MK and LK and for NK and PK. So I'll start with MK. MK should be to LK as NK is to PK. Let's see if that's true. MK is not 2, it's not 8, it's 8 plus 2. And PK, let's see, LK would be from here to here, 8. equals NK, which is this plus this, PK plus PN, so that's 12 plus 3, over PK, which is 12, smaller triangle. So this gives us 8 plus 2 is 10 to 8, equals 12 plus 3 is 15 to 12. Now, if these are equal ratios, and they're proportional, then we can use SAS to say that these two triangles are similar. Reducing 10/8, we can reduce that by 2. 2 goes into 8 4 times, and 2 goes into 10 5 times. 15 twelfths reduces by 3. 3 goes into 12 4 times. 3 goes into 15 5 times. So we do have the same ratio, 5 to 4 equals 5 to 4. Therefore, triangle MKN is similar to triangle LKP by the side angle side similarity theorem. And by the way, the scale factor is 5 to 4.